Hi, so I told you at the end of the last video that in this next video I would work you through the calculations of finding the population standard deviation and the sample standard deviation for this set of numbers. So here's how that works. First thing we have to do is find the mean. And we actually did that. This was one of the examples in the last section. We added these 10 numbers together and they added up to 800, and then we divided by 10, and so the mean was 80. So that's the first thing. We need the mean. The mean is 80. Then step 2 is for each value, we need to subtract that value minus the mean. So 81 minus 80 is 1. What's 83 minus 80? 3. What's 86 minus 80? 6. And so on down the line. What's the last one? What's 35 minus 80? Well, it's negative 45. Now, by the way, if you were to add these numbers together, they would add up to 0. So you don't have to add them together, but if you want to check that, just the score minus mean, before you square them, just these individual numbers, some of them will be positive, some of them will be negative, and they should add up to 0. But now we're ready for step 3, and that's where we square each of these differences. So each of the numbers in this column gets squared. That is, it gets multiplied by itself. 1 squared, 1 times 1, is 1. 3 squared, 3 times 3 is 9. 6 squared is 36. 2 squared is 4. 3 squared is 9, and so on. Now be careful. What is negative 45 squared? If you put it into your calculator like this, negative 45 squared, the calculator will give you negative 2025. But that's not the correct answer, because the calculator is interpreting this as meaning negative 45 squared. In other words, negative 45 times 45. It's doing the squaring before it's doing the negative. But that's not what we want. We want to take the number negative 45 and square that number, negative and all. And so it does come out to be positive 2025. So since we knew it was going to have to be positive, I could have just put it into the calculator as 45 squared. Just leave out the negative because I know that squaring is going to kill that off anyway. So it's not negative 2025, it is positive 2025. Okay, do you remember what we do next? What's the next step? We're adding up all of these squares. So we're adding 1 plus 9 plus 36 plus 4 and so on. And these numbers add up to 2,346. By the way, notice the reason this number is as big as it is mostly because of this last row. If it wasn't for the 35 that gave us this 2025, this would not be nearly as big as it is. So when we get our final answer for the variance and the standard deviation, it's going to be as big as it is mainly because of this one score that's so much different from all the others. Most of these scores are fairly close to the mean, but this one is a lot further away. And so it's making the greatest contribution to the variance and the standard deviation. Okay, now we're ready for step 5. That's where we take this total, and if we're working with a population, trying to find the population standard deviation, we just divide by the total number of values, which is 10. So 2,346 divided by 10 is 234.6. And if what we wanted was the variance, that would be it. The population variance is 234.6. But remember, it asked for the population standard deviation. So to get that, there's one more thing we have to do. Remember what that is? We have to take the square root of this number. So the square root of 234.6 is 15.3166576, and really the digits keep on going, but that's as much as the calculator is showing me. But if we round it to one place after the decimal point, it's about 15.3. So that's the answer to the population standard deviation, 15.3. Now, if we wanted the sample standard deviation, what would we do differently? When we get to this point, we've added up all of these, and then we divide by n minus 1. N stands for how many numbers there are, which was 10 in this example. So n minus 1 would be 9. We're dividing by 9. So 2,346 divided by 9 is 260 well, really 0.666 and so on, but it's about 260.67. And then when we take the square root of that number, we get about 16.1 after we round to one decimal place. So the sample standard deviation is 16.1. Now, earlier I did post a video showing how you could use the statistics capabilities of a calculator, an Excel spreadsheet, or something like that to give it a list of numbers and ask it to give you things like the mean and the median and the standard deviation. And I showed you how you could use Excel, put in the numbers, and if you want the population standard deviation, the function for that is stdev.p. So that's what I have here, the standard deviation for a population of the numbers in A1 through A10, and Excel does say it's 15.3, and then the standard deviation for a sample of those same numbers in A1 through A10, Excel tells me that that is 16.1. And as an experiment, let me go in and change this 35 to maybe an 85, so it's a lot closer to all the other numbers there. So I'm changing the 35 to an 85, and look what happened to the standard deviation. It went way down. Now it's more like 3 point something instead of 15 or 16 point something. Because now all of these numbers are a lot closer together. In fact, if they were all the same as one another, like if they were all 81, the standard deviation would be 0 because there's no variation at all. They're all exactly the same as each other and as the mean of all of them. Now, if you look in your book or you've learned how to calculate standard deviations before somewhere or something like that, you may have seen these alternative or shortcut formulas that give you another way of calculating the variance and the standard deviation. They are algebraically equivalent. So if you really wanted to, you could work through all the gory algebra details of showing that the formula we were working with is really mathematically equivalent to what we've got right here. So they do give you the same final answer. They're just a different way of getting that final answer. So I'm not going to devote a lot of time to these, not going to really explain how they work, because they give you the same answer. They're just another way of doing the same thing. But if you've learned about them somewhere else, or if you want to try using them instead, you can. They're just another way of calculating the variance and the standard deviation that is mathematically equivalent to the procedure that we talked about. Now, the standard deviation of a set of data values or a variable measures how much variability there is. The bigger the standard deviation, the more variable, the more different those data values are from one another. But sometimes you have two different sets of data, two different variables, maybe even two different kinds of things measured in two different units or measurement scales, and you want to compare them. That's where the coefficient of variation comes in. That lets you compare the variability of different sets of data, like height versus weight, or height of people versus length of ants. After all, a 1-inch difference isn't all that much of a difference if you're talking about people. One person who's an inch taller than another person, not a big difference. You might not even notice it. But one ant that's an inch longer than another ant, that's a pretty big difference in ant scale. So there's more variability in ants that are an inch apart in length than there is in people that are an inch apart in height. So coefficient of variation kind of takes that into account and lets you compare different kinds of things. And the way it's calculated, you divide the standard deviation by the mean and then multiply by 100, like you're converting it to a percent. Remember to do the division in this order. Standard deviation first, divided by the mean. That means that usually you'll be doing the smaller number divided by the bigger number, which tends to throw some people off, but that's the way you do it for coefficient of variation. So, for example, among the men in a certain town, the average height is 67 inches with a standard deviation of 3 inches, while the average weight is 178 pounds with a standard deviation of 20 pounds. Which is more variable, height or weight? Well, you can't just say that a standard deviation of 20 is bigger than a standard deviation of 3, because 20 is 20 pounds and 3 is 3 inches, and can't really compare them. But you can calculate coefficients of variation for the height and the weight, and then compare those. So for the height, the coefficient of variation is the standard deviation divided by the mean. So 3 inches divided by 67 inches, make sure you get it in that order, and then times 100. And that comes out to be about 4.5. For the weight, the coefficient of variation, when you take the standard deviation divided by the mean, that's 20 divided by 178 times 100, and that comes out to be 11.2. So which is more variable, height or weight? Well, it's the one with the larger coefficient of variation, weight. There's more variability in how much these guys weigh than there is in how tall they are. Okay, we got one or two more things to talk about, so I'll come back and get to those in part 3 of this video series for section 3.2.